Okay, let's start this week by continuing discussion about the four-quadrant DC-DC converter. By the way, for the students that are interested in the lab activities, I can confirm that there is the lab next week, Tuesday afternoon at 2:30 p.m. Okay, led number 4. 3 labs for 3 weeks, the 4th, the 11th, and the 18th of May. Okay. The next step for coming here to do lab is to book your seat through the student portal. Okay. There is a tab which is called prenotazione lezione or something like that. Okay. Go there and then simply book with your name, etc., etc. Okay, this is for makes possible to enter the building. Okay, because you have to prove that you have, let's say, lecture or lab or whatever. Okay, so please, students that are interested now must book their seat in the lab. Okay, so the booking is active now, so you can do this even today if you want. So we just talking about the four-quadrant DC-DC converter, which is normally called full bridge or also H bridge. Okay, you can see there are 2 legs. Okay, I put here IGBTs, but you can have also MOSFET, and they are organized in such way that you have 2 nodes A, B, through which you can have your load, that in this case is the DC motor. The switching activities of the 4 switches are driven by a pulse width modulator that on the basis of a voltage control that you can have at the input side, generate the 2 switching function QA and QB, and Q not A, Q not B, that drives all the 4 switches. You should know that we have here 2 kinds of pulse width modulation. One is called the unipolar pulse width modulator, and the other one is called the bipolar pulse width modulator. And we're talking about the unipolar pulse width modulator. So let's continue this discussion. Remember what I showed you last time. So the unipolar pulse width modulator is also called the 3-level pulse width modulator, depending on the control voltage. If the control voltage is higher than half the value of the peak of the modulator triangular voltage, okay, higher than this, then the output voltage V0 average value is positive, and the entire waveform instantaneous of the output voltage V0 is positive. Okay, so it's unipolar in this sense. So let's consider again this case. Now let's start the analysis by just looking what happens to the output voltage V0, which is positive and totally positive, we can say. For example, you can have, say, a waveform like this. We learned for previous lecture that the period of this waveform is twice the switching frequency. This top level is Vd, this lower level is 0. Okay, so the average value is positive, and it is represented by this dashed line here. What happens when you have the first interval in which V0 is higher as Vd, that you have, for example, Ta plus and Tb minus that are on. Okay, we also learned that there is a difference between devices that are commanded to be on or off, so where they are commanded to be closed or open circuit, and the device that conducts the current. So there is difference between devices that are on, off, or conducting devices, the current, okay? So they can be different. So what I'm saying here that in the first interval, TA plus and TB minus are on. I don't know if these devices conduct also the current, okay, but for sure they are on. In this second part, you have that TA minus and TB minus are on. Then you have TA plus and TB minus again, providing you the output voltage VD. And in this last interval, you get 0 by a different status of the switch with respect to the previous interval. So TA plus, TB plus. Okay, so you get always TA plus and TB minus on when you get VD at the output, but then the level 0 can be obtained by closing both the low side switches, or even here, what happens here is both the high side switches. Okay, so there are different. So the sequence is exactly the sequence that you can see here. Okay. So let's consider what is the behavior of the current I naught flowing through the load. Okay, and as you remember for our previous discussion about the two quadrants converter, there can be different solutions. Okay, for example, you can have a current I naught which is totally positive, and so the average value is also positive. So current which has this average value here, and also the current is totally positive. Something like this. So this is the first case. Let me call 1. So I naught positive, and then you can have that I naught minimum and I naught maximum are both positive. Okay, just you remember how can you get this value. Okay, remember that the discussion here is to say we got an exercise to quadrant converter exactly estimating this, say, behavior of the current. The basic assumption here is that I can replace all the switching power pole at the node A and B here, okay, replacing a circuit which is a circuit, let's say, having a DC value and an average value. Okay, so V not average and V not instantaneous value. Then you can have L, R, and the back EMF. Also, the current has an average value plus an instantaneous value, okay, which is also AC contribution, let's say. And so if you want to get the average value, you have to take into consideration only the DC quantity. So this is the average value V naught, RA, and EA. So basically, the average current is V naught average value minus EA over RA. Okay. So just exactly as we did for the previous exercise for the two quadrant converter, I can have different, say, possibility for V naught, okay, because V naught average value depends on DIA minus dB multiplied voltage VD. So depending on the duty cycle, remember, V naught is that equivalent duty cycle multiplied VD, and this equivalent duty cycle can be, let's say, positive or negative, okay? And so I can modulate this value here in order to have a current that can be an average current that can be positive or negative. In order to do that, the back EMF should be positive, okay? If the back EMF was, say, negative, say this sign here, which is not a difference, is, say, a summation, is a plus, and so you cannot have a current, an average current that can be, say, can be modulated because it can be negative, okay? It's only positive. So this is the way, so this analysis, I consider that the back EMF is only positive, meaning that the back EMF is related to the rotational speed. So it only positive means that, for example, the motor is running the clockwise direction, okay? And this happens for the average value. What happens for the AC contribution, so the blue curve for the current? Then you have to consider in this cycle just the AC contribution. So the voltage V0, the inductance, and then you have to skip the back EMF. Okay, so here the slope is given by is the V D minus V0 average value divided by L, and here the slope is negative V0 average value over L. So nothing new, the same reasoning that we previously done for the two-quadrant exercise now happens here. What can be analyzed is the status of the conduction. So what are the devices that conducts that current, okay? So in order to do that, let me just use these circuits in order to understand that here you have a current which is positive. So the current is flowing exactly as indicated. So the current goes, say, from the left to the right into the DC motor. And in the first situation, the switches, in this first interval, the switches that are on are TA plus and TB minus, okay? So you can say that TA plus and TB minus are on. So the current is positive, where the current can flow in the circuits, okay? So the current is positive, meaning that the current can go here, can return through the motor, and then go into TB, returning to the source. So in this situation, in which the current is positive and TA plus and TB minus are on, the current is also conducted by TA plus and TB minus. Okay, so devices that are on in this situation also conduct the current. What happens when you have TA minus and TB minus on, so the second sub-interval during TS, TA minus and TB minus on? So let me just cancel out this arrow here. So now the devices are TA minus and TB minus that are on, okay? The current is again positive, and the current can be conducted by what? Not by TA minus, okay, because this is off, TA plus, sorry, because this is off. Not by TA minus, because the current cannot go from the meter to the collector in the IGBT, but it can be conducted by the diode. And then when return back from the motor, the same current can be conducted by TB minus. So dA minus and TB minus now are conducting the current. What happens in the third subinterval? But this subinterval is the same as the first one. So because we have TA plus and TB minus on, the current is positive. So again, TA plus and TB minus. Then we have a fourth say interval here, in which we have TA plus and TB plus on. So in that situation, you have now the devices are the I side devices that are on. Okay, the current is again positive. And so in order to provide the current path, the current can flow through TA plus here, then returning from the motor, this current can go not to TB plus, because TB plus cannot accept current from the emitter to the collector, okay, but it can go through TB, returning to the source. So TA plus, TB plus. Okay, this happens when you are in that say number one situation. Okay, this is not the only possibility, because, for example, you can have a situation in which the average current is positive, but not all the instantaneous current is positive. And this is the situation number two. So average current is positive, the peak current is positive, but the minimum value of the current is negative. Let me just have this something like this is not the best drawing I can add, but okay, you have IO minimum, which is negative, and IO maximum, which is positive here. The average value is positive. So in that situation, we have the standard fourth sub-intervals into the switching period TS, okay? And in each of these four sub-intervals, then you have other intervals in which the current is positive and when the current is negative. For example, here you can have this time T star in which the current is negative. Okay, so we have TA plus and TB minus that are on, but the current is negative. So let me do consider this situation, which you have a current which is negative. The current negative means that the current, say, is entering the node A, so it's exiting from the motor. And then you have TA plus and TB minus that are on. So what are the devices that conducts this negative current? But you can see that this current cannot be conducted by TA plus because the current cannot go from the emitter to the collector, so the current can go to the diode. Here the current goes in this direction, and in order to makes possible for the current to flow, you can see that the current cannot flow also in TB minus, okay? But it can flow through the diode dB minus. So now we have dA plus and dB minus that conducts the current. So here, dA plus and dB minus. What happens from T star to T switch divided by 4, which is the first interval here? TA plus and TB minus are on, the current is positive, so we have exactly the same behavior that we studied in the situation number 1. Okay, so here you have TA plus and TB minus. What happens from TS divided by 4 to T double star? The current is positive, TA minus and TB minus are on, so the situation is exactly the same that you can have here. So it is TB minus, dA minus. Now we have a different situation from T star to TS divided by 2, because now TA minus and TB minus are on, but the current is negative. So let's see what happens here. Okay, now the current is negative. We have TA minus and TB minus that are on. The current, which is negative, can be conducted by, let's see what happened here, by TA minus, because it's in the correct direction from the collector to the emitter to be conducted. And then for TB minus, you can see that the current can be conducted again by the diode TB minus. Okay, so here you have TA minus, TB minus. TA minus, DB minus. Okay. What happens in the third subinterval? The third subinterval is the copy, is the same of the first subinterval, exactly the same. So we have this first part, in which you have dA plus and dB minus, and the second one, which you have dA plus and dB minus. Okay, and then so we can go directly to the third subinterval. The first subinterval as a first part, which the current is positive, so we can say get the result that we previously analyzed, TA plus and dB plus, and then we have another subinterval into these four intervals in which you have negative current. Okay, so TA plus and TB plus are on, but the current is negative. So we need to analyze it a little bit in detail. So now the diode, the transistors that are on are TA plus and TB plus. The current enters the node A, and so in order to do that, you have to accept current flowing not through TA plus but TA plus here. Okay. And here you not have this current flowing here. The current goes here and goes through TA TB plus. Okay. So it's TA plus TB plus. Okay, and this is the sequence that you can have. Of course, this situation is together with the situation number 1, we examined before, a situation in which you have average voltage which is positive, average current which is positive. So you are providing power from the switching power pole, so from the VD source to the motor. Okay, so you are in what is called the motoring operating mode. P naught is positive. So if you want, we are operating our DC motor in the I not, B naught, for example, this is the plane, in the plane in which you have just positive current and positive voltage. So you are here. Okay, so you are in the first quadrant of operation. Of course, there are other situations that I just can mention here. For example, when you have, and then it's the third situation, in which you have voltage which is positive, and in the unipolar pulse width modulator, a positive average output voltage means totally positive instantaneous voltage, P naught. And then your average current is no more positive, now it's negative. Something like this. For example, this situation, not the total instantaneous current is negative, because, for example, IO max is positive, but IO min is negative. Okay, so you have this situation. Or then you can have the situation number 4, in which the current has a negative average value, but also a negative instantaneous value. Okay. In that situation, we have B naught, which is positive, I naught average value, which is negative, meaning that the average output power is negative. So we are in the braking operating mode. Since EA is defined to be positive, or to have this behavior, it means that the rotating speed is always, say, positive, so the motor is rotating counter clockwise direction, but we are in the motor is braking. Okay, it's reducing its speed. This situation in terms of devices that conduct the current are analyzed in the same exact way we did for the situation number 1 and number 2. Okay, so if you look at the plane I naught average value, V naught average value, now we are in this part here. Okay, this is also called forward braking. Okay, because the motor is going forward, so it's going, so rotating in the same direction as before. And this is the previous one was forward motoring. So now here in this quadrant number 4, okay, that you can have. What are the devices that conducts the current? Okay, you can look at the discussion we had before, and then we have the same reasoning. Okay, so when TA plus and TB minus are on, then you have a part in which the current is negative and a part in which the current is positive. So you have again here DA plus and DB minus, and then you have TA plus and TB minus there, etc., etc. You can go on. When the current is totally negative, then you have just DA plus and DB minus for the entire interval, and then you have TA minus and DB minus here, etc., etc. So you can derive all these devices that conduct the current by the previous analysis. No surprise here. Okay, just we are enlarging the part which the current is negative with respect to the part in which the current is positive. Okay, because we are reducing the average value. Questions about this, say, discussion here? The way I derived this device that conducts the current, or the way I drawn this variable, whatever. Okay. This is for a unipolar pulse width modulator having the average output voltage V naught positive. Okay. Because we have the control voltage, which is exactly higher than half the value of the triangular voltage. So let's analyze what happens when you have that the control voltage now is less than the peak value of the triangular voltage. This leads to an average value of the output voltage of the bridge, which is negative. Okay. So in that situation, in the unipolar pulse width modulator, the total instantaneous output voltage V naught is negative. Okay, so you can see that the waveform is something like this. The period is Ts divided by 2, so it is exactly twice the switching frequency. And see what happens for the current. Of course, we have, again, 4 different cases. Okay, so this is the number 1. The number 1 is that I naught is totally positive as an average value, but also the instantaneous value. So I naught max and I naught minimum are both positive. Okay, so what happens during the first interval? The first interval has a negative VD voltage, and this is obtained by TA minus and TB plus on. The second interval has 0, and this is due to making TA minus and TB minus on. Negative VD again, TA minus, TB plus, and here you have TA plus, TB plus. Okay, this is the correct sequence for getting a negative average value. Okay, how you can modulate the average value of the current I naught from positive to negative? Okay, with the same model we described before. We have to take the equivalent circuit at the DC, and so this means that you have to consider the average value of V naught, and then you have to consider the back EMF. Okay, is the difference between the average value of V naught and the back EMF that can be modulated. And in order to do that, since the average value is V naught is negative, it means that also the back EMF should be negative. So in that situation, the motor is rotating, let's say, counterclockwise. So the direction of the rotor is exactly opposite as before. Okay, so what happens here that you have this behavior, the slope is due to the AC contribution of the circuit, so it's negative VT minus the average value, which is negative, so plus V naught over L, and here is plus V naught. Let me go to the get me the absolute value here. Okay, so nothing new, but now the circuits to be analyzed in order to see what are the devices that conducts the current is a little bit different from before. For example, in the previous situation, when the output voltage was, say, positive average value, there is no the combination of the switch TA minus TB plus, which is now is present. Okay, so TA minus TB plus is something that is new now. TA minus TB plus. This is the combination of the switch that provides you to have negative VD as the input-output voltage V naught. The current is positive, so the current goes from, say, the node A into the motor. And so what are the devices that conducts this positive current? But as you can see here, the current is positive, so the current goes in this direction, go into the diode, goes here. So DA minus conducts, then goes in this direction. And when you go to TB plus cannot accept this current, the current goes to dB plus. So DA minus and dB plus. Okay, I have a question. Let me just answer this question. Exactly. Marco Simonetti asked if in this case, in order to have the average current positive, as indicated in this draw, we have that the back EMF in absolute value should be higher than the output voltage. Exactly, because you have to consider always, let's say, these equivalent circuits for getting the average quantity. Okay, there is one in which you have just the DC contribution. Okay, so the current can go in one direction, the opposite direction, depending on the value of these two batteries, okay? And so, which is that provides you exactly this behavior. So what is happens during the third interval? It is the same because Ta minus dB TB plus, so we can put immediately here the behavior. What happens in the second interval? In the second interval, we get Ta minus and TB minus, and the current is positive, okay? But this is a situation that we already analyzed, okay? Because we have Ta minus and TB minus, and the current is positive is something that we already get here, for example, in this part, okay? So we have TB minus and DA minus. TB minus and DA minus. What happens in the fourth interval? We have, let's say, 0 as output voltage, so TA plus and TB plus, and the current is positive. Again, this is a situation that we already know from previous analysis because it's the situation that you have now here. So TA plus, DB plus. Okay. Then you have again the situation number 2, which the current is positive, but the say not the wall current, instantaneous current is positive. So for example, the maximum, the peak value is positive, but the minimum value is negative. So you have I naught, which is positive, but the current has some something like this. The minimum value is negative, the positive, the maximum value is positive. Okay? So here, the only unknowns are in this interval in which the current is negative. So what happens in the current is negative. We have Ta plus, Ta minus, and Tb plus. So let me just clean up. Now the devices that are conducting are Ta minus and Tb plus, but the current is negative. So the current is negative means that the current is going in this direction. Okay, it enters the node A, so it goes in this direction. If it enters in this direction, we can see that it is the diode dB plus that conducts the current. The current goes in this direction, and so the current goes sorry. The current has this direction here, so the current goes into Ta minus here, so going here, and here is dB plus. So Ta minus TB plus. I have another question from Antonio Moles. In the first case, when TA plus and TB plus are on, it's not dB plus that conducts the current. What I said before. Let me check. TA plus and TA plus and TB plus. So we are just considering the previous. Just let's say finish this one, and then I come back to the one that you asked for. Okay. So here we have TA minus and TB plus. Then when the current, sorry, here, the current is negative, TA minus and TB plus. Okay, when the current is positive, you have TA minus and TB plus, etc. for all the other part, because it's something that we already know. Let me just consider the case indicated by Antonio Moles, TA plus and TB plus. So you are considering let me, sorry, clean up the screen to avoid positive current. So the current goes in this direction. Then I have TA plus and this one, TA plus and TB plus on. The current is positive. The current goes from TA plus, going here. This is the current goes in this direction, then goes here, and then goes in dB plus. What I said before. dB plus, okay, TA plus, dB plus, sorry. Is it already, is something that I put also there? Let me check, TA plus, dB plus, okay. Thank you for your say, it's correct. I think that I miss simply to complete the plus in the drawing, okay. All other segments that you can have in this current part can be derived from, say, previous analysis. Okay, so no problems here. In both the situation, we have a negative voltage and positive current. So if you have a plane of the average current and average voltage, now you are in a negative voltage side and the positive current side. You are occupying this second quadrant. Okay, the average power in both cases is negative, and so you are in the what is called the reverse forward braking mode. So we are in the motor which is rotating in the counter, for example, clockwise direction. So the direction of rotation is inverted with respect to the previous case. And now we are, say, absorbing power. The switching power pole is absorbing power from the motor. So we are decelerating the motor, okay? There is another other two graphs that arises when you have negative voltage, okay, and also negative average current. Let me just sketch these cases. We have again negative voltage. TS over 2, negative VD 0. Again, we have TA minus TB plus, TA minus TB minus, TA minus TB plus, TA plus, TB plus. The current can be, for example, I naught average current negative, but not the total current is negative. For example, you can have something like this. Okay, so the maximum current is positive, the minimum current is negative, but the average is, let's say, negative. Okay, so this situation can be analyzed and studied exactly as we did before in order to find out which are the, say, conducting devices. One, two, that was the third, and then we have also the situation which the total current is negative. In that situation, both the average current and the average voltage are negative. So the average power now is positive. So we are providing power to the motor. So we are in the, say, motoring condition. Of course, motor operation mode, operating condition. Of course, we are motoring, so we are providing power in order to make the motor to rotate counterclockwise, so reverse direction with the situation that we have before. So this is the reverse motoring operation. In terms of the quadrant, we are in the situation which both are negative. So we are here, the third quadrant operation. Okay. So this is we can say about the unipolar pulse width modulator in the 4-quadrant converter. By the way, students of power electronics maybe can see a basic difference between the behavior that we analyze in the 2-quadrant converter and in the 4-quadrant converters in terms of the current flowing through the load. Okay, that students maybe remember that in DC-DC converter that are not bidirectional, like the, say, what we studied in that course, the buck or the boost, etc., the operating condition can be divided further into continuous conduction mode and discontinuous conduction mode. Okay, in continuous conduction mode, the current through the load was always positive, and the current through the load is negative, or sorry, is null when you go into the discontinuous conduction mode. Here, there is no distinction between continuous conduction mode and discontinuous conduction mode. For example, here, okay, you can see that the current is negative but continues to flow because there is a device that can, say, support and have current flowing, which is, let's say, bidirectional switches that I used in my switches. Okay, so there is a large portion of the current that goes negative, so the current is not zero. So there is, even here, the current is totally negative, but they continue to flow. And that the same behavior what we have in the situation which the total current is positive. So no more distinction between a continuous conduction mode and discontinuous conduction mode for this bidirectional converter. Okay, the current can flow always, okay, because we employed a bidirectional devices, bidirectional semiconductor switches that are able to support current flow in both directions. Okay, this is just a parenthesis for that students that learn something in power electronics course. This is the unipolar pulse width modulator, but remember that, as I said at the beginning, okay, we also have another pulse width modulation case, which is the bipolar pulse width modulator. Okay, so let's analyze by using the graph the behavior of the bidirectional for quadrant converter modulated as bipolar pulse width modulator. Remember that this is also called the two-level PWM, which is the main difference in this kind of modulation with respect to the unipolar one. Remember that while in the unipolar one, you have basically one total control voltage, the control voltage V control. And from that, you can derive the control voltage for the leg B by having that V control voltage of the leg B is the difference between the peak value of the triangular voltage, V triangular peak minus V control. And the two control voltages for the leg A and B are symmetrical in value with respect to V triangular peak F divided V triangular peak value divided by 2. In the bipolar pulse width modulator, we have just the same control voltage for the leg A and the leg B. So here, the basic consideration is that the V control that we have to use as an overall command at the input of the modulator is at the same time the control voltage for the leg A and also the control voltage for the leg B. Okay, this is what happens here. So let's have a look to what happens in a practical situation. Okay, so let's have our modulator waveforms, and this means that I have my triangular voltage, like here, for example, V triangular peak, and then also the value V triangular peak divided by 2. This is TS, etc. Okay, this is V triangular in the modulator. Then we have the control voltage. Let's start with the situation in which the control voltage is higher than V triangular peak divided by 2. So here. So this is the control voltage. Since the control voltage is higher than V triangular peak divided by 2, I'm expecting that the average output voltage should be higher than 0. This is the control voltage, the total control voltage, but this is again the control voltage for the leg A, and this is the control voltage for the leg B. Now I'm using the same control voltage for both. So let's see what happened at the unitary switching function QA for the leg A. What I have to use? I have to use the comparison between the blue card control voltage for the leg A and the triangular waveform. And which is the law of generation of the unitary switching function, the standard usual law that we already employed in the past. Okay, when the control voltage is higher than the triangular one, then you get QA, which is 1. Otherwise, it will be 0. Okay, what happens here? That here you have the TA plus is on. When it's 0 means that TE minus is on. TA plus is on, etc. How can you generate the unity switching function? And now there is the second big difference with respect to the unipolar pulse width modulator. I again have to use the comparison between the blue curve, the control voltage, which is also the control voltage for the leg B, and the triangular wave. But I have to invert the generation, the law by which I generate the unitary switching function QB. In this case, when the control voltage, blue curve, is higher than the triangular voltage, I get 0. Otherwise, I get 1. So here we have T B plus on, here, sorry, T B minus, TB minus, TA plus, TB plus. Okay, I'm putting here the name of the transistor that will be on in that specific interval, okay? What about the output voltage? But the output voltage is simply the difference between the two unitary switching function multiplied by VD. So in that situation, I have, let's say, VD minus 0, so you get VD. Here I have 0 minus VD, so you get minus VD, negative VD, VD. Okay, so something like this. So what about the average value of this waveform? But if you look at the positive, say, interval, for example, this one, is larger than the negative one, when you get the average value, the positive quantities overcomes the negative one, so the average output voltage should be positive. Exactly as expected here. This quantity is exactly dA multiplied Ts. This dB quantity is dB multiplied Ts. Okay, so how it, which is the, say, the width of the output pulses in the output voltage? We not, but it's simply, say, dA Ts, this part, and dB Ts, this negative part. Which is the switching frequency of the output voltage. The switching frequency of the output voltage is exactly Fs. If you compare this situation with the situation we analyzed for the unipolar pulse width modulator, we can see that previously in the unipolar pulse width modulator, the output voltage has a period which is Ts over 2. So it is twice the switching frequency. Here, the harmonics of the output voltage are exactly at DC value, Fs, 2Fs, etc. Okay, so if you want to consider the output spectrum, for the bipolar, you can get the output voltage, and this is dAA minus dB this is, let's say, K-pole. Let me put in this. K-pole is KPWM multiply V control minus VD. This is the average value. And then you have Fs 2fs, 3fs. So you have harmonics at say integer multiple, all the fundamental one. Okay. So this is something which is different from say unipolar pulse width modulator, which you have the DC contribution, then you have harmonic just 2fs, then 4fs, etc. So here the harmonic contribution is say higher, so you have more harmonic content, you have more harmonics in the output. So this means that, for example, if you want to filter out having the same filtering that you have in the unipolar, here you can have the filtering action at the output, the modulator action is a little bit more difficult. Here it's not so effective like in the unipolar pulse width modulator due to the presence of, for example, this harmonic here. So it's a little bit more easy to filter out the harmonics in the unipolar pulse width modulator, having the same switching frequency, etc., etc. Another difference with respect to the unipolar pulse width modulator is that the output voltage is not unipolar. As you can see, the output voltage has one level, which is VD, and another level, which is negative VD. So you have two levels, and this is why this modulation is also called two levels. Okay, we have not the zero level. And then in that situation, you can have simultaneously the positive value and a negative value. So it is bipolar. Okay, this is not what happened in the unipolar pulse width modulator, in which depending on the output voltage, average value, positive or negative, you can have total positive voltage or total negative voltage. Okay, that situation was, say, unipolar voltage. This is what happens for V control, which is higher than V triangular peak. What happens when you have the control voltage, which is less than half the value. But in that situation, let me just see the comparison between the control voltage and the triangular voltage. This is V triangular peak. Then I have V divided by 2. Suppose that my control voltage now is here. Okay? This is the V control, which is V control for the leg A and also V control for the leg B. So let's see QA. No surprise, QA is the usual derived waveform. QB QB is obtained by using the same control voltage, so the same comparison, but with an opposite generation law. So we have to consider that at this time interval, QB now goes from 0 to 1. Again, we have TA plus here, TB plus here. Okay, so what happens to the output voltage? The output voltage has a behavior that can be obtained exactly in the same way. So we have to take the difference between the two unit switching function multiplied by VD. And so you get VD and then negative VD. something like this. As you can see now, the negative contribution here is larger than the positive one, so the average value is negative. But basically, the waveform is, say, the same as before. Is a bipolar triangular voltage, rectangular voltage, having two levels, positive VD and negative VD, that switches at, say, having the duty cycle derived by the unitary switching function, as said before. The only thing is that this contribution here is a contribution which is narrow with respect to the previous one. Okay, the switching frequency is again the frequency of switching of the output voltage is the switching frequency Ts, and so we have the same behavior as before. Looking at this situation, okay, at these two different situations I considered before, now is appear evident from this discussion and also this one that there are just two possible combinations of the switch in this bipolar, say, modulation, that are Ta plus and Tb minus and Ta minus Tb plus. Say only two combination, so Ta plus Tb minus and Ta minus Tb plus. The first one leads to having V naught, which is equal to Vd. The second one, which is for V naught negative Vd. Okay, so we have just two combinations, A and B, if you want. If you compare this situation with the previous one, unipolar pulse width modulator, then we have Ta plus and Tb minus, then you have Ta minus and Tb minus, Ta plus and Tb plus, and Ta minus and Tb plus. So we have four switch combination. Now we have just two. Basically here, in this bipolar circuit, okay, the bipolar switch, the two transistors that are connected in this way, Ta plus and Tb minus, and also Tb plus and Ta minus, always are commanded to be on or off simultaneously. Okay, so you have that Ta plus and Tb minus and Ta minus and Tb plus acts as they were a unique switch, okay, that are commanded to be on and off simultaneously. This is not what happened in unipolar pulse width modulator, which we have combination also of Ta plus and Tb plus, and also the low side switches Ta minus and Tb minus. Okay, there are two possible combination of the switches. Let's, to conclude this discussion, see what happens in terms of the blanking time or dead time. Remember, we need to avoid the simultaneous conduction of the switches in the same leg, because we don't want to short circuits the supply. Okay, this was analyzed in the two-quadrant converter. Okay, and we learned that we need to delay a little bit the rising edge, so the turn on of the transistor, in order to have more space between the turn on and turn off instant of the two switches in the same leg. Okay, in order to avoid, say, superimposition of the two conduction of the switches. And this means that they have to insert a time which is called T delta, which is exactly the dead time or the blanking time. For example, we know that there is a variation delta V, I don't know how the name I give it, maybe V epsilon, something like that. So we have a variation of the output voltage in the leg of the two-quadrant converter, which is given by negative T delta over Ts multiplied Vd, when the output current this is the current that I call IA was positive, or positive T delta over Ts V delta when the current is negative. No? This happens for the two-quadrant converter. But now we have to do the same thing. We have to delay the turn on instant with respect to the turn off. So we have to a little bit delay by T delta. But now we have two legs. So we can exploit the results we already know from the two-quadrant converter, and then we use this result to find out what happens in the four-quadrant converter. In the four-quadrant converter, we have two switches. Let me put in the ATL A and B here, okay? And this is N. Then you have also diodes. Like here, okay? So I know that for just one leg, this result is correct, because this is what happens for the two-quadrant converter, and two-quadrant converter is basically, say, one leg of this four-quadrant converter, okay? But the same happens for the other leg. So we can have the same, say, result that we previously derived analytically also for VBN. And we can say that we have negative d delta over Ts multiplied with d, or plus d delta Ts multiplied with d, and Vd is this voltage here. This is when IB is positive, and this is when IB is negative. Okay. Now we try to relate delta VAN with delta VBN, with this VBN here, VAN is here. Okay. The current IA is also the current I naught in this four-quadrant converter. While the current IB is negative I naught. What happens to the output voltage? But the output voltage is the difference between VAN and VBN. Okay, so we can use these relationship that are due to the Kirchhoff current law and voltage law at the output of this four-quadrant converter to relate these results here. So we have delta V, and also the variation that you have in the average value of the output voltage due to the presence of this that time is simply delta VAN minus delta VBN average value. And this is when the current is sorry, this is negative. I exchange. When the current is negative, you get and when the current is positive, is this one. So what happens when the current is negative means that IA negative is IO negative, okay? And IB negative, it means that you have negative IO negative. So basically, when you get the difference, you can get due T delta over Ts multiplied with D when the current is positive, or negative due T delta over Ts with D when the current is negative. I have to be checked if this is positive or negative. Maybe you in the slide. I remember that this was the opposite, but I can change. I don't know what. Let me. I have to check you in the slide. Maybe you can do tomorrow. But basically, I think that the correct one is this one. When the current is positive, then you have a negative R. I don't remember well. I have to derive from the scratch. I do remember. I don't use memory. I have to derive it. Okay, but anyway, we can check tomorrow. But what happens is that you have, let's say, a number 2 here. Okay, then tomorrow we will check what happens exactly in the condition for by which these are true or not. Okay, but here the situation that you have this average value, which have a number 2 here, due to the fact that you have to make the difference between the output of the two half bridge, okay, of the two legs, and this leads to this correction, okay, twice that you can have in the 2-quadrant converter. Okay, if you have a question, I can answer now, of course. Basically, I just have to check these inequalities. Antonio Molas asks, which are the reasons to use unipolar or bipolar pulse width modulator? Basically, the reason are, say, in the output spectrum that I can use. Okay, this is one of the main reasons. Okay, because I said that one of the main difference, maybe the most important one, is that you can reduce the harmonic content at the output for the unipolar one. Okay, so in that situation, in which you are requiring very high quality of the output voltage, okay, so basically you want to be an effective filter reaction at the output, then the unipolar pulse width modulator can help to, say, have a better filter action. In all the situation in which your filter characteristics are not so good, because your L or your R of the motors are not known, or maybe they are, say, not so, they doesn't not give a pole that makes possible to reduce the harmonic content. Having a spectrum in which the first high order harmonic is twice the switching frequency can, say, helps. Okay, remember that the switching has a direct impact in the ripple of the torque. Okay, so maybe situation in which your motor has a very low inertia and you are searching for something that filter out high order harmonics, the unipolar pulse width modulator can help. The drawback is that you have a little bit more complicated action for your switch, because you have 4 different switch combinations instead of having just 2. Okay, tomorrow we have a specific example in which we compute the ripple that you can get, the maximum ripple you can get for the output current for unipolar and bipolar, comparing the two situations. And it will be clear that for unipolar pulse width modulator, the ripple you can have at the output with the same filter at the output is less than that you can get in the bipolar one. So this can help. Okay, so thank you. We can see each other 11:30 a.m. Bye.